Hi, I'm Dane Quinn from the University of Akron. For today's video lecture, you can probably guess the topic because you can see the title. Today we'll be talking about the response of single degree of freedom systems. The classic example of a single degree of freedom system is shown here on the right. It's a spring mass damper system. We have a mass, or a block of mass M. We have a spring on stretch length L and stiffness K. We have a damper, damping coefficient B. And when we choose to measure the response of the system from the unstretched position of the spring, the equation of motion is given here as mx double dot plus bx dot plus kx equals 0. So we've already given a lecture that basically derives the general solution. And what we found was that this response can be written as the sum of two pieces. One of those pieces is C1, e to the lambda 1 t. And here C1 is an arbitrary constant, while lambda 1 is a property of the system. And then the second piece is C2, e to the lambda 2 times t. So lambda 1 and lambda 2 are both properties of the system. In particular, they solve this characteristic equation, m lambda squared plus b times lambda plus k is equal to 0. This is great, right? Because this is quadratic in lambda, which is the unknown. And so we know the solution. We can go back and use our quadratic formula, and we can actually write that as minus b over 2m plus or minus then the square root of all of this other stuff. So this may not look completely familiar to you, and if it doesn't, that's okay. I'd pause the video lecture right now and go back and try to kind of get your quadratic equation and your solution into this form. It's a little bit of algebra, but it's relatively straightforward. Now that you've done that, you've paused the video, you've worked through that algebra, I want to notice a couple of kind of interesting things here. In particular, I want to notice that we really just have two groups of parameters. Right? So if you notice, we have b over 2m, right, which sits here, but it also sits inside this square root. And then the second group of parameters that we have is this one here, k over m. So we'll identify this first group as sigma. So sigma is b divided by 2m. And then this second group we'll identify with omega n. Right? So in particular, omega n is going to be the square root of k over m. When I do that, I can rewrite these solutions to this characteristic equation as lambda 1 or lambda 2 is minus sigma plus or minus the square root of, well, again, there it is, sigma squared minus, and then since omega n was the square root of this, this is just omega n squared. In addition, when we go back and rewrite the characteristic equation in terms of these two parameters, we see that it reduces to, actually we can factor out an m, then we have lambda squared plus 2 times sigma times lambda plus omega n squared equals 0. And again, we basically just factored out an m from all of these terms. In terms of sigma and omega n, you can show that b is the mass times 2 sigma, right? So just solve this for b. And k is the mass times omega n squared. All right, just solve this for k. So if you notice, we started off with 3 physical parameters. And those were m and b and k. Right, the mass, damping, and stiffness. And what we found is that the response only depends on 2 parameters. After all, I mean, this is the response, x of t, given here. And that depends on lambda. And lambda can be written in terms of sigma and omega n alone. Right? So these 3 physical parameters combine into two response parameters, namely sigma and omega n. Okay, so I'd like to look and see what happens to these values of lambda, right? After all, they're really important. How do they vary as our response parameters change? The important thing is that I have this square root term, right? And inside the square root is sigma squared minus omega n squared. Now, that can be positive, so that the square root is real. It could be 0, or it actually could be negative, in which case, when I take the square root, I would get a complex number. So very different things happen to our system as we vary these response parameters. And really, it depends on whether or not lambda is real or complex. So let's look at those cases. And here, I'm going to assume that m and b and k are all positive, so that sigma and omega n are likewise positive. Here, if sigma squared minus omega n squared is greater than 0, well, that implies that lambda 1 and lambda 2 are real. And in particular, we'll note that sigma is always greater than sigma squared minus omega n squared, right? Because this quantity is only less than sigma squared. So these things are not only real, but they're negative as well. So let's go and kind of plot those on our real and imaginary complex plane. Right, so I'll note the point here that is at minus sigma. Then these two, we'll call them eigenvalues, are at minus sigma, and then plus this quantity and minus this quantity. Right? So I might have 1 over here at lambda 1, and then I might have the second lambda 2 over here. I'll go in and just sort of draw a line where this value of minus sigma is. So the distance of these two values of lambda from this point at minus sigma, kind of the center, is this distance, which is the square root of sigma squared minus omega n squared. Right? So again, if the eigenvalues are real, they're centered at minus sigma and then, sort of equally distributed on either side. The next case that we'll think about is when sigma squared minus omega n squared actually vanishes. So in this case, lambda 1 equals lambda 2, and that's equal to sigma. Right? So I go up here. If this quantity vanishes, then I have two roots. So I have a root of multiplicity 2 at minus sigma. Right? So in this blue case, sigma 1 equals sigma 2, and it's located right there at minus sigma. The last case we want to look at is arguably the most interesting case. So that's going to occur when sigma squared minus omega n squared is actually less than 0. So in this case, lambda 1 and lambda 2 are complex. To make our lives a little bit easier, if this quantity is negative, then we'll write lambda 1 and lambda 2 as minus sigma, plus or minus, and then we'll actually kind of flip this. So it's omega n squared minus sigma squared, so that this quantity is positive, and the fact that this overall quantity is negative is kind of now explicit. And so then we'll write this as minus sigma plus or minus I times omega d, where omega d is defined as omega n squared minus sigma squared. And in this case, if sigma squared minus omega n squared is negative, then omega n squared minus sigma squared is positive. So this is known as the damped natural frequency. And we'll see that in a later slide. Going back to our complex plane, now we have two roots, real part minus sigma, and then imaginary part plus or minus omega d. Right, so I might have one up there and one there. So we'll call this lambda 1 and lambda 2. Now, just like we identified when the eigenvalues were real, right, the magnitude of the complex part is just square root of omega n squared minus sigma squared, right? Or omega d. So in either case, this kind of point minus sigma is kind of the center of our eigenvalues. If they're real, they're oriented left and right, both real. And if they're complex, right, then we have one at minus sigma plus omega d I, and minus sigma minus omega d times I. So a little bit more about this. Well, here they are again, right? I've written lambda 1 in terms of the physical parameters, but then in terms of sigma and omega n, also omega d there. And what I'll note is that we can actually do a little bit more. So this value of lambda, let's do some algebra to it. In particular, I'm going to factor out k over m, square root of k over m, from this whole expression. So now this first term becomes minus b divided by, well, 2m times square root of m over k, square root of k. So that reduces to b over 2 square root of km. And then plus or minus the square root. Now, a little bit of algebra. You can pause this, but again, you'll find that this quantity now appears again inside the square root. And because we factored out k over m, square root of k over m from the entire thing, then this piece just reduces to 1. So now we have we have an additional group, namely this. So in fact, we can write this as omega n, which was square root of k over m, and this group we'll call zeta. So it's zeta plus or minus, in this case, zeta squared minus 1. And here, zeta is known as the damping ratio, and it's b divided by 2 square root km. So again, if we want to relate all of these parameters, well, I have the natural frequency. And there, omega n is defined as the square root of k over m. And I have the damping ratio. So zeta is b divided by 2 square root of k over m. And then I have the damped natural frequency, which we saw before. And there, omega d can be seen to be, well, it's, in this case, going to be omega n square root 1 minus zeta squared. And in terms of the physical parameters, right, that reduces to k over m minus b divided by 2m. Remember, inside the argument is basically the negative of this, so that we pull out that factor of I. Finally, we can identify this group as the decay rate. So the decay rate is defined as sigma, which is zeta omega n. And again, in terms of the physical parameters, that's b divided by 2m. The real advantage to identifying the damping ratio is that when I look at this expression for lambda 1 and lambda 2, the question of whether or not these values are real or complex really only depends on the damping ratio itself. So if I know the damping ratio, I can tell a lot about the response of the system. And of course, the damping ratio is just a function of the system parameters. So let's look at those three cases again. If the damping ratio is greater than 1, then this quantity is real. And as a result, lambda 1 and lambda 2 are both real, so that the solution is real, right? So again, we call this an overdamped system, right? So if zeta is greater than 1, then both of the eigenvalues are real. We typically assume that lambda 2 is less than lambda 1, which of course is always less than 0. Once again, the general solution looks like, well, there's an arbitrary constant, c1, and then e to the lambda 1 t, and an arbitrary constant c2 with e to the lambda 2 t. Both of these decay exponentially in time, because lambda 1 and lambda 2 both have negative real parts. Over on the right, I have basically illustrated kind of an example case, right? So let's assume that x1 is in green and this second part is in red. Here I've chosen c1 to be negative and c2 to be positive. As a result, the general solution is the sum of these two things, right? So x is x1 plus x2. Again, we add these two together to get the overall response, right? So doing so, we see that initially it drops, and then it just sort of decays to 0. Now, this term with lambda 2, because it's more negative, it actually decays faster, leaving the response to be dominated by this slower decaying solution that corresponds to lambda 1. Again, if I go back and look at this plot, in the complex plane, lambda 1 is actually closer to the origin, so it decays slower than lambda 2, which is further away. Now let's turn to the interesting case, and that's an underdamped system when zeta is between 0 and 1, so that these values of lambda are now complex. So again, in this case, lambda 1 and lambda 2 are complex. And with omega d defined as, well, we can do this a couple of different ways, omega n squared minus sigma squared, or omega n times 1 minus zeta squared. Then lambda 1 and lambda 2 can be written as minus sigma plus or minus I times omega d, which in terms of the natural frequency and damping ratio reduces to omega n times minus zeta plus or minus 1 minus zeta squared. Our two solutions reduce to x1 as c1, and again, this is an arbitrary constant. e to the minus sigma plus I omega d, and x2 as an arbitrary constant. We'll call that C2, e to the minus sigma minus I omega d times t. Here we have exponentials with complex exponents. That physically is kind of a little problematic to deal with because ultimately we want a real solution, right? We don't want a solution that has complex parts. So we can actually reduce this to a real solution using Eulers identity. Right, so let me remind you, Eulers identity is e to the ix is cosine x plus I times sine x. And if C1 and C2 are complex conjugates, right, so C1 is C2 bar, right, bar indicates the complex conjugate, then we can write this general solution as x of t is e to the minus sigma t. Notice that there's an e to the minus sigma t in each of these terms. And then this C1 and C2, right, these arbitrary constants, they can be rewritten as a, just an amplitude, times sine omega d times t, plus b times cosine omega d times t. Once again, we've taken these two arbitrary constants, C1, C2. If they are complex conjugates, then the solution reduces down to a purely real function. We can now combine these two harmonic pieces into sort of a polar form. Right? So now we have an amplitude, e to the minus sigma t, and this reduces to sine omega d times t plus a phase shift. We can relate this amplitude back to A and B, and here we find that the amplitude squared is A squared plus B squared. And then the tangent of this phase is actually B divided by A. Right, so this is just a little bit of trigonometry. Maybe you can pause the video and kind of work this out. It involves angle addition formulas and that kind of thing. So here, again, the response decays exponentially. And it decays with a decay rate of sigma. So exponential decay, and the rate is sigma is zeta omega n. And it oscillates with frequency omega d. Which is the damped natural frequency. Again, up here I have basically illustrated an example, right? So x1 here is going to be b e to the minus sigma t. It's going to be the cosine term, and I have chosen b to be positive, right? x2 in red is the sine piece of this, and here a is negative. So if I go and combine these two, basically I add them together to get the overall response. And the overall response will look something like this. Right, so it decays exponentially with the same frequency, but a different amplitude. And notice that I can actually draw an envelope for this decay. And this envelope here is what's out front here in this polar form. Right? So this envelope is the amplitude e to the minus sigma t. Now, what about these arbitrary parameters? Well, they are used to fit initial conditions. Right? So either A and B or x and theta are used to fit initial conditions. So let's work that out, at least for maybe these values a and b, right? So if we take this form for the general solution, then the initial position, right, let's say is x naught, right? So that's going to be x at time 0. And x dot naught is going to be x dot at time 0. So these are very general, right? These are the most general initial conditions we could have, right? Some position, some velocity. How do we evaluate A and B? Well, I will essentially go up and substitute in t equals 0 and figure out what this reduces to. When I do that, e to the 0 is 1, sine of 0 is 0, and cosine of 0 is 1, right? So this is simply b. For the velocity, well, now I have to take the velocity of this term, the derivative of this term, and again evaluate at t equals 0. Okay, so when I do that, let's take the derivative of this term, right, times this, plus this times the derivative of this term in parentheses. Okay, so the derivative of e to the minus sigma t is minus sigma. And then when I evaluate e to the minus sigma t at 0, I get 1. And then this piece evaluated at 0 gives me b. Doing the same, this is 1, and then I take the derivative of what's inside, and I get plus a omega d. So I have these two equations. I have x0 equals b, x naught dot is this quantity, and I just want to solve for a and b. Well, that's easy enough. In particular, b is super easy. B is equal to x naught. And then solving this second equation then for a, we find that a is x naught dot plus sigma times b, well, b was x naught, divided by omega d. So we're able to solve for the arbitrary constants given the initial conditions. And of course, we could do the same procedure using the amplitude and phase. Or, once I know this, I can go and find the amplitude and phase from these relationships. So what's left? Well, it's that case in the middle. And that was a critically damped system. So zeta is equal to 1. Now, in this case, lambda 1 equals lambda 2, which equals minus sigma. Of course, sigma was zeta omega n. Zeta is equal to 1, so this actually just reduces to minus omega n, natural frequency. And the solution takes the form x of t is, it's a little bit different. It ends up looking like c1 plus c2, c2 is again arbitrary, times t, e to the minus omega n t. And here I have gone and given an example of these two pieces. Of course, the general solution is the sum of those. C1 here is negative. I've chosen it to be. C2 I've chosen to be positive. So when I add these together, right, I end up with a solution that looks like this. Right? Again, I'm just adding these two terms together. Once again, the response decays exponentially in time because of this exponential function that's part of the solution. I can match initial conditions, just like I did with the underdamped case. Well, x naught is x0, which in fact just reduces to c1. X naught dot is x dot times 0, which again, taking the derivative, setting time equal to 0, gives me C2 minus omega n times C1. And so I can solve for C1 and C2. C1 is equal to x naught, and C2 here is x naught dot plus omega n times x naught. So these are those three cases. We had started off with an overdamped system, so that's zeta greater than 1, so that we get real solutions. Then I did an underdamped case where I get complex solutions, and we see that the response oscillates as it decays. And then finally we did a critically damped system so that the two values of lambda are actually identical. The last thing we want to talk about is the decay rate. Basically, how fast does the response decay away? In all cases, the response decays exponentially, assuming, of course, there is damping. Right? And in fact, the response decays precisely because of damping. And remember that the damping ratio was B divided by 2 square root Km. Now, the overall decay rate is actually determined by the slowest decaying mode. It's kind of like a chain. How strong is a chain? Well, it's only as strong as its weakest link. And how fast does the response decay? It only decays as fast as the slowest decaying mode. Right? So here I've got two solutions. One of them is C1, e to the minus omega nt. And then I've got a solution that has an extra factor of time out front. For an underdamped system, both of these two modes decay at rate sigma. And then finally, for an overdamped system, I again have these two modes that decay at different rates. So if we have an underdamped system, right, so again, that's going to be zeta between 0 and 1, then the real part of these values of lambda is simply zeta omega n. So when I go and plot that, again, we're just looking for zeta between 0 and 1. Then this decay rate just increases linearly as the damping ratio increases. Right? So, here we would get a response that just decays exponentially in time. And for an underdamped system, again, as we add more damping, we decay faster. For a critically damped system, so this is the case where zeta is equal to 1, then the real part of lambda 1 and lambda 2 is simply equal to omega n. Both of these terms decay at exponential rate omega n. Right? So that's going to be given here as this point at zeta is equal to 1. And then finally, if zeta is greater than 1, we have an overdamped system. And the real part is equal to omega n times zeta, and I'll write this as minus plus, because again I've got this negative sign, zeta squared minus 1. Notice that I have two solutions here. Right? I have one solution that is positive but relatively small, and then I actually have another solution that's really large. So both of these terms decay exponentially, but the question is, which one dominates? Well, the one that dominates is the one that decays the slowest. Right? So if I look at the overall response here, right, I have this slowest decaying mode, which is given, say, here. And I also have a fast decaying mode. But again, as time goes by, the fast decaying mode decays, well, fast, leaving only the slowest decaying mode. Right? So in this case, this would be our lambda 1, and our lambda 2 is way up there. So if I look at the overall decay rate for our system, it's going to follow the lowest value of this curve. Right? So for an underdamped system, there's only one choice. And then for an overdamped system, right, it follows lambda 1. So one thing to note is that critically damped systems decay the fastest. Adding more damping beyond critical damping actually causes you to decay slower. As an example, you could think about, say, an oscillator moving through air or moving through something really viscous like honey, say. If it's moving through air, then maybe the system's underdamped, right? There's not a lot of damping present in the system, right? And so we just oscillate and decay slowly. Maybe that's over here. But if we're moving through a viscous material like honey, it's got so much damping that the system can't return back to equilibrium very rapidly, right? There's just too much viscosity in the fluid for our system to come back to equilibrium. And so it actually decays very slowly. It's only this intermediate value of critical damping that gives us our fastest decaying response. And here I will note that for a desired decay rate, there are actually two values of damping that give you that decay, right? One happens to correspond to an underdamped system. So again, there's not a whole lot of damping, right? You don't decay very rapidly. And the second corresponds to an overdamped system, right? There's so much damping, right, that it takes a while to get back to the equilibrium position. So in general, this is how systems decay as we vary the damping, right? Remember that the damping ratio, if K and M are fixed, can be identified with B. So there's some intermediate level of damping that gives us the fastest decay. So that's our system response as we vary the different parameters. And what we noticed is that by introducing and identifying damping ratio and natural frequency, we really can characterize the system response in terms of overdamped, underdamped, critically damped. If there's not a lot of damping, system oscillates and decays. If there's too much damping relative to critical, then the system just decays exponentially. So that's it. We'll do more problems like this, and in particular, once we begin to model single degree of freedom systems, ultimately things will sort of come back to this same picture and the response that we've developed here in this lecture. So that's it. Thanks a lot. I'm always looking for comments. Please leave feedback. You can send me an email. I welcome your thoughts. Thanks so much. Take care.